Are we ready for TPU time? All right, let's go. Start streaming TPU time. We're going live. We're going live. We're live. We're live. We're live. Okay. All right, everybody. Hello world, it's Siraj, and welcome to my live stream on the TPU, the Tensor Processing Unit. In this live stream, I'm going to talk about the technical details of what a TPU is. I'm also going to do a short demo of, it's going to be a benchmark comparing the CPU to the TPU. And then I'm going to do another benchmark comparing the GPU to the TPU. And at the very end, we're going to do some natural language processing. This is a default example that was provided by Google, and we'll go over that at the very end, okay? So this is a live stream. Let's start off with a 2-minute Q&A. This is the structure for this lecture, and that's how we're going to go. Hello, everybody. We've got deans in the house. We have a very vibrant community that we're building. Every single day is another day that's part of the School of AI. Okay, so 2 questions, and we'll get right into this. And I want to preface this by saying this will be a technical lecture. Okay, we're talking about systolic arrays. We're talking about hardware. It's going to be awesome. I'm very excited for this lecture. Okay, so the first question here is. A TPU who has used Google's Colab? We all have. And the second question is it like the USB thing that Intel made? Yes, in that it is called an ASIC, an application-specific integrated circuit, okay? Now that's it, and hi Chris, Freemind, Wafa, and College Guide, and Mel's and Pooja. Hi everybody. Okay, now straight into this. Let's get into this. Why did Google make this thing, right? I mean, there's GPUs out there, there's CPUs out there. NVIDIA is doing a great job. Shout out to NVIDIA, by the way. This is nothing against NVIDIA. I love NVIDIA. They are awesome. But this TPU thing is pretty cool. So what's happened at Google is that there has been a giant demand for deep learning over the years. Let me just make this small. Okay. That's a good question, but okay. So the demand for neural networks and deep learning has grown over the years at Google, and TPU development actually started in 2013, which is 5 years ago. This is a long time ago in the machine learning world, and it's been used in production since 2015. Okay, so deep learning has been super important at Google. All of their products, the ones that we know and use every day, search, translate, photos, Gmail, the Google Assistant, all of these products use deep learning. Okay, and so what deep learning is we have all of these machine learning models, right? We have random forests, we have support vector machines, and one of them is a neural network. And when we give a neural network a lot of data and a lot of computing power, we call that deep learning. And that has outperformed almost every other machine learning model almost every time, like 99% of the time. And so they use it. It's so crucial to all of their products, right? So that's the key here. Deep learning is absolutely crucial to Google. Okay, so why did they make their own chips, right? We can do deep learning on a CPU. We can do deep learning on a GPU. Well, there's been so much progress in machine learning over the years, right? In just the past few years, every single benchmark, right, whether it comes to image classification, whether it comes to video generation, whether it comes to so many different use cases, deep learning has outperformed everything else, and we've seen new state-of-the-art results in each of these subfields of machine learning. And so why deep learning? Well, if we were to plot out the amount of data and the performance of a model, the red line here are traditional learning algorithms. They kind of plateau after a while, right? The performance can only get so good based on how much data you give it. But neural networks, and that's what the acronym NN stands for, neural networks, if you give them a lot of data, they will start outperforming everything else, as you see here, the small, the medium, and the large. So it's a game changer, okay? So, and what are neural networks? Well, I have so many videos on what neural networks are, but briefly, neural networks are models created with linear algebra. So linear algebra is the name of the game, okay? Linear algebra is awesome. Neural networks are just a chain of matrix operations applied to input data. There's actually a wrap for this. Input times weight, add a bias, activate, repeat. Input times weight, add a bias, activate. So that just keeps going and going and going at the basic level, right? And we can think of that input data, image, video, whatever it is, as a matrix of numbers. and we give it to this black box neural network that's doing this series of operations, and we get a result. Right, so if it's an image is actually a matrix of pixel values between 0 and 255, and we feed it to this very simple neural network here, which is just the equation y equals mx plus b, where m is actually the weight, so it's w. So y equals wx plus b, where b is a constant, it's a bias value. And so we are just taking that input image, pre-processing it such that it becomes a vector, multiplying it by our weight, adding a bias, and then adding an activation function, which is actually not listed here, and the output is our prediction. Now, like I said, they're just a series of matrix operations. But it turns out, so when it comes to hardware is tailored, current CPUs and GPUs, they're tailored for specific types of operations, right? Multiply. There's a specific literal piece of hardware dedicated to multiplication, and another one to division, and another one, so all of these math operations. Well, it turns out for neural networks in particular, what we're doing is we're continually performing the same set of operations over and over and over again. So what it comes down to is a giant matrix full of numbers. All of them are being multiplied in parallel. So it all boils down to multiply a bunch of numbers together and add the results. So we can think of this as a single operation, which we can call multiply accumulate, or MAC. And so if there was a hardware level construct dedicated to a multiply accumulate operation, then we could start computing even faster, right? So we're slowly building on the ideas here that got Google to create a TPU. And so Moore's law, invented by Gordon Moore, it's a founder of IBM in the 50s, he said that computing power would double every 2 years. And that so far has held true. But not IBM, Intel. And so was it actually Intel, Moore? Was it Intel or IBM? I got to check my facts here. I always mess up these. More was Intel. There we go. Anyway, great. Intel at 50. I got the 50 part right. Anyway, back to this. This is live, by the way. So many things can go wrong here because it's live, but that's how we do. So Moore's law is plateauing. And so we've got to find a way around this. Well, Google definitely has to, because all of their products and profits depend on it, right? So how do we get past the limits of Moore's law, the limits of what hardware can do for us for deep learning? So now we're going to get a little more technical here. Okay, so a CPU is a scalar machine. So a scalar is a single number. These are linear algebra terms. Like I said, this whole talk is going to consist of only linear algebra. There's no calculus. There's nothing else. By the way, neural networks are models built with linear algebra and then optimized with calculus. We'll just talk about calculus like for 1% at the very end to talk about a certain type of optimizer specific to the TPU called a cross-shard optimizer. We'll talk about that at the end. So a CPU is a scalar machine. It accepts single values. So it processes instructions one step at a time. So they can perform matrix operations, but they're not in parallel. They're sequential. And Moore's law is coming to an end. So that's a CPU. Now, a CPU has multiple cores, and each of these cores contains arithmetic logic units. It's got a control structure. It's got cache memory. It's got a DRAM. It's got memory associated with it. What a GPU is it's similar to a CPU, except it has multiple cores, like hundreds of cores. So while a CPU has 4 cores, a GPU has hundreds of cores. Now, why does this matter to us? So GPUs were designed for 3D game rendering, which involves a lot of parallel processing, right? Shading, ray tracing, pixel values. There are all these things that are happening at once in these 3D games. They require parallelism. So what GPUs do is they are optimized for parallel operations on numbers. Okay, so to get a little more technical, here are a list of attributes for both a CPU and a GPU, and we'll just talk about 2. CPUs are for low compute density, whereas GPUs are for high compute density. By density, we're talking about groups of numbers being operated on simultaneously, right? So matrices, vectors, whereas CPUs are sequential, okay? So to get more technical, we can think of, if we think of a CPU as a scalar machine, we can then think of a GPU as a vector machine, where a vector is a one-dimensional array of numbers that can be operated on at the same time. And so GPUs are general purpose chips, right? They don't just perform vector operations. They can really do any kind of operation, although they are optimized for vector operations. So how do we improve upon a GPU that does well with vector operations? Well, let's just look at what we're doing with the GPU here very quickly, how it works, and then we'll go into TPU specific code. So we're going to just perform this simple matrix operation here. So check this out. I just want you to look at this matrix operation. What this is, it's a matrix operation that says multiply this scalar number 2 by this matrix, okay? And so what linear algebra, okay, so just quick primer here. So algebra is a mathematical, it's a branch of math that is dealing with scalar numbers, right? Single numbers. But when it comes to operating on groups of numbers at the same time, matrices, we need a different set of rules, right? So do we multiply the 2 by the 10, then add that to the 10 by the 4, or do we do 2 times, right? So there's not a very, if we just look at this without looking at the rules of linear algebra, we'll be kind of confused. But when we see this diagram, we see, oh, okay, linear algebra tells us that when we multiply a scalar by a matrix, we're just taking that scalar and multiplying it by each of those values, and that's the output value. So that's one of the rules of linear algebra, of which there are many. So let's do this in MXNet, which is a very short, just want to make sure everything's all good. Good, okay, everybody's in here. So let's do a very short demo in MXNet. It's just a few lines of code. And I just want to show, and this is basically CUDA, by the way. I'm so excited for this. Okay, so this is basically CUDA. Let me just install MXNet, and while it's installing, I'll explain what is happening here. Import as MX. Let's make sure that we are doing this on the GPU first. So the runtime is going to be the GPU. Good, it's the GPU. Now let's install this. So what this is, MXNet is this open source library. Let me just say, I like TensorFlow better, but I'm just doing this because it's a very simple 3-line of code example that we can use to demonstrate what a matrix operation looks like on the GPU. And so what MXNet is doing in this case is we're going to create a single object called an ND array, right? An n-dimensional array. And so that is the construct, the object in MXNet that's going to represent a matrix that we're going to use to perform this operation in 3 lines of code. Okay, so while this is loading, in fact, let's do this. So what we're going to do is we're going to say A, the result, is going to equal mx.nd, an n-dimensional array, dot ones. Now ones means that this is going to be a 2 by 3 matrix. So this is going to be a 2 by 3 matrix of just ones. All those values are ones. It's a 2 by 3 matrix, and all those values are ones. We're going to do this on the GPU, and then we're going to say B is equal to A, so that entire matrix, times the scalar number 2, and let's just add 1. And then we'll return that back as a NumPy array. So this is MXNet, but it's basically CUDA. It's a very thin wrapper over CUDA, which is NVIDIA's GPU-specific programming language. CUDA is awesome. It's all about optimizing. It's super hard, but I really like CUDA. I just want to say that. Anyway, so we have installed. Still going, so it's going to take a while, and then we can do this. So like I said, we're taking a 2 by 3 matrix of ones, saying on the GPU, multiply it by the scalar number 2, and return the result as a matrix, as a NumPy matrix, and here it is. So that is a very simple GPU operation that we just performed. Okay, so I just wanted to show that, and now let's do a little Q&A before we get into the TPU part. Everything's a-okay, thank you. Any questions? Okay. I don't understand a thing in RL math. Is it okay? Yes, it's okay. I mean, everybody starts out not knowing a thing about whatever topic they're learning. So of course, that's okay. Look, we're trying to grow the amateur research community here, and we are just at the very beginning. We are at the very beginning of this revolution of growing the amateur research community. We at School of AI deeply believe that anybody can do research. They don't necessarily have to be a part of academia. They don't necessarily have to be a part of the industry. We believe in growing the independent amateur research community, and we think that with the democratization of tools like Collab, like TPUs, like all these technologies, it's going to become easier and easier for everyday developers to make valuable contributions to the field. So it doesn't matter. It's all about growth. I'm growing, I'm learning. This thing could just totally fail, right? The TPU in Collab is actually, it's kind of like beta-ish. It was messing up for me last night. So who knows if this is even going to work, right? This could totally fail. So we're all learning and growing at the same time. One more question. Does TPU support only TensorFlow? Yes, it only supports TensorFlow. Great. That's it. Now, the TPU itself. So Google actually has built 3 generations of these TPUs now, okay? So the first one was in 2015, the second one was in 2017, and the third one, it just came out this year. And also a TPU pod is what they call a cluster of these TPUs combined together. It's called a TPU pod, okay? So it took them 15 months to make TPU v1, and that is actually very fast. Because what the TPU is it's an application-specific integrated circuit, or ASIC. Now, if you're familiar with Bitcoin, ASICs are used to mine Bitcoin, not GPUs generally. Why? Because ASICs are custom-made chips designed specifically, in that case, to mine Bitcoin. Now, can we apply the same logic to deep learning? Of course. What if we created an application-specific integrated chip, an ASIC, not a general-purpose chip, specifically for the matrix operations that neural networks require? What would we call that? Well, we would call it a TPU, a Tensor Processing Unit. Now, the downside of this are that TPUs are inflexible. ASICs are inflexible. Once you build that chip using, say, let's say for the matrix accumulate operation, the MAC, right? Specifically for neural networks. Now, it's not going to be able to do individual, like different operations. It's only going to be able to do that hard-coded operation, the MAC, that we hard-coded into it, right? So it's a specific chip, specifically, I said specific like 3 times now, specifically for deep learning. And there have been 10, and so here's a great image of it. I should have been showing this. The multiply, add, accumulate step looks like this, right? So we have our multiplier, we're multiplying A times B, we add our bias, and then we accumulate the results, and then we have our output. So that's kind of a diagram of what the MAC structure looks like. And so Google decided they needed to make a matrix machine, right? GPUs are vector machines. They can also be applied to matrices, and CPUs are scalar machines. But matrices are 2-dimensional sets of numbers. And actually, they need more than just a matrix machine. They need a tensor machine, because what is a tensor? Can anybody answer the question? What is a tensor? You watching. Okay, so if you said that a tensor is an n-dimensional array, you are correct. A tensor can be 1 dimensions, 2 dimensions, 3 dimensions, 4 dimensions, 5, 6, hundreds of dimensions, because each feature in a data set can be considered a dimension of data. Now, we just can't visualize it with our biological brains, but that's a different topic. So they wanted to design a chip specifically for matrix operations, and what we're seeing here is the TPU chip, right? So it's got 4 independent chips, and what this is, it's a diagram of a single chip. So each chip has 2 compute cores called tensor cores, just like this. And inside of each core are 2 different units. One is for operating with scalars and vectors, and the other is called the MXU. That's specifically dedicated to the multiply accumulate operation that we talked about, or matrix units, MXU. It's also got 8 gigabytes of on-chip memory, the HBM, with each tensor core. And they can perform 16,000 operations in each cycle, and these cycles are happening in parallel. We're going to get into this. They even decided to use a different type of floating point representation called bfloat16 rather than the standard IEEE half precision representation. And so what this allows them to do is execute user computations independently. And it's got a high bandwidth interconnect that allows these chips to communicate with each other directly. And we're talking about the TPU pods that I mentioned earlier. So what this pipeline looks like is we have a neural network model that we build with what's called a TPU estimator. Estimators are the application level construct in TensorFlow associated with models. So they built one specifically for the TPU. Why? Because when we build one with the TPU estimator, it will then compile down using XLA, which is this custom proprietary software that Google has built that allows it to be run in the form of a systolic array. Now you might be thinking, well, what's a systolic array? We're going to get right into that in a second, okay? So the XLA is an experimental compiler for the back end of TensorFlow, and it turns your TensorFlow graph into linear algebra, and it has backends of its own to run on CPUs and GPUs and TPUs, and it's proprietary. But we'll see how that goes. So the systolic array, we're just going down the rabbit hole here, guys. We are going so down the rabbit hole before we start coding. Let me see if there are any questions. Cool. Okay, so the systolic array, what this is it's a kind of hardware algorithm. The systolic array is a type of hardware algorithm that describes a pattern of cells on a chip that computes matrix multiplication. How do these cells on this chip perform the matrix operations that a neural network requires? So systolic, the word systolic is derived from the I think there's Latin for wave. It's Latin for wave. And it describes how data is moving across the chip. It's moving across the chip in waves, like the beating of a human heart, which is kind of cool and kind of scary, but cool mostly. So here's an example here, right? So we have these two matrices. We multiply them together, and here is our output. And this output is going to be computed using a systolic array algorithm. Okay, so for this 2 by 2 input, each term in the output is going to be the sum of two products, right? So A and E, we're going to multiply those two together, and it's going to be the sum of A and E plus B and G. So if you stare at this image for a while, it'll start to make sense, the ordering with which these operations are happening. So let's say that A, B, C, D represent our activations, and E, F, G, H are our weights. So for our array, we're going to first load up the weights like so. So E, F, G, H are going to be loaded up. And our activations are going to go into an input queue, which for our example will go to the left of each row. So we need to apply our activations to the result of our weight operations. So we're going to take our input data, multiply it by our weights, and then apply our activations to it. And we want to do this in parallel. So what the systolic array algorithm does is it allows multiple cycles of computations to happen in parallel. So what's going to happen is each cell will execute the following steps in parallel, 4 steps. The first step is to multiply our weight and activation, and it's going to be coming in from the left. And if there's no cell on the left, take one from the input queue. Add that product to the partial sum coming in from above. If there's no cell above, the partial sum is going to be 0. Pass the activation to the cell to the right. If there's no cell to the right, throw away the activation. Pass the partial sum to the cell on the bottom. If there's no cell on the bottom, collect the partial sum as the output. You might be thinking, and those are the 4 steps of a cycle, and many cycles are happening in parallel. You might be thinking, what did you just talk about? That's a very valid question. So I also have a Python example specifically for you right here that demos exactly what a systolic array looks like, but we have a lot to cover here. So we're not going to go over this entire code, but definitely check it out. Well-documented code, not written by me, but very well-documented code. Check it out. So by these rules, what tends to happen is it looks like this. The wave of data is moving to the right and down simultaneously. So it's a wave that's coming down like this. So we actually have a GIF that demos this. This is Google's GIF, right? So it's like, watch this. So it's starting at the top left, and the wave of operations is moving. It's spreading in the right and downwards directions like that. Okay. So what happens is, normally, to compute a matrix operation, it's going to take a sequential solution. So on a CPU, would take n cubed time, where this takes n cubed cycles, where n is the number of cycles. So this is the performance. Whereas on a TPU, it's going to take 3n minus 2, which is a very peculiar performance metric, but that's what it is. It's 3n minus 2 as opposed to n cubed, which is a huge performance, right? Especially at scale. So, like I said, this is what it looks like. It's going to the right and it's going down. That's the flow of data on the TPU hardware chip. So it's just MAC operations, multiply, accumulate, multiply, accumulate, multiply, accumulate at the same time in parallel, massively parallel. And so the high density of these systolic arrays lets Google pack in 16,000 of them into a single MXU. That's a lot. That's a lot. And what this translates to for us is a lot more speed and efficiency when we're training our neural network, both for inference and for serving, right? So, not inference and for training. So that's it. The rest of the chip is important and worth going over. But the core advantage of the TPU is this MXU unit. It's a systolic array matrix multiplication unit designed specifically for neural networks. So what are use cases? So we've seen some benchmarks here and there, but I don't think that we need to question whether or not the TPU is a faster chip than a GPU for neural networks, right? Because Google uses it for Google search, right? Just think about how massive Google search is. There's no question that a TPU is faster than a GPU specifically for neural networks. That being said, do not underestimate Jensen Huang and NVIDIA, because I promise you they are working on something just as good, if not better. So it's all love, it's all family. We're all in this together. So that's anyway. Anyway, so CPUs are, what are the use cases for each? We have CPUs, we have GPUs, we have TPUs. CPUs are good for quick prototyping, very simple models. Think linear regression, right? Think just very small amounts of data. Performance doesn't matter. You just want to do something really quickly. CPUs are great for that. Small, think small, right? Small effective batch sizes. It's not going to take a long time to train, like that. Just like that. So, but GPUs are good for models that are not written in TensorFlow, right? Because you can only run TensorFlow code. Think about the XLA compiler I talked about for TPUs. So there's that, and so medium to large models, great for GPUs. But TPUs are great for TensorFlow-made models that are dominated by matrix computations, neural networks. And we're talking giant models that takes weeks or months to train. What would be one great example? Machine translation. Okay, I think I remember reading a machine translation paper, and I'll take questions after this, so start asking questions. I remember reading a machine translation paper that talked about, I think it was a bilateral recurrent network, and it took them a week to train. Machine translation takes so much data to train. It took Google a week to train Google on their computer. That's insane. So that is a perfect use case for a TPU, right? Now let's take some questions before we get into our benchmarks. Okay, DeepMind's AlphaGo has brought down from 176 GPUs to 4 TPUs. Yeah, so AlphaGo used TPUs for sure. Nick, systolic arrays sound like a very fundamental data structure. They are a very fundamental algorithm for sure. One more question. What else can a TPU do other than specific jobs? Or is it that a TPU is that limited? And I only know basic algebra. What can I do with this math in RL? Great question. So first of all, TPUs are made for neural networks. And what else can you do besides neural networks? You can You can try to do other things, and there's some research there actually. You can make some valuable contributions by trying new types of models out, but they are designed for neural networks. For your second question, and that's it for the questions for now. When do we use linear algebra in reinforcement learning? Look, you and me are neural networks. We are neural networks in our head. Okay, we are neural networks. But we are neural networks in the context of a Markov decision process. This reality is a reinforcement learning process. We can frame reality mathematically. We are agents in an environment. We are in a specific state. And we're trying to optimize for the next, what is going to be the best next state to be in? What is the best next state to be in, right? And the way we get there is by performing the next best action that's going to optimize for a reward value. So we, neural networks, are inside of a Markov decision process. So reality is deep reinforcement learning. So what you'll find is that it's not about should I study RL or should I study supervised or should I study unsupervised? No, it's all a part. They're all pieces of the same puzzle. So it all matters. Anyway, let's get into our benchmark here. So for this benchmark, we're going to do a simple add operation. Now look. No promises this is going to work. This is kind of beta, and it didn't, it worked, and then it didn't work last night, so we'll see if this works. But we're going to perform a simple TensorFlow-based add operation on the CPU, and then compare that to the TPU. We can all use the TPU because it's inside of Google Colab. Okay, so let's start with this. So our first step is going to be to import our dependencies. We have OS, which stands for operating system, which lets us do some, input output and, file retrieval and things like that. TensorFlow time NumPy, great. And we'll install these dependencies. Okay, now let's do a CPU benchmark here. Let's write out our operation. So like I said, this is going to be a very simple add operation. We'll call it add op. Okay, add op. So add op is going to take two scalar values, x and y, and it's going to return what happens when we add them together, just like that. And so x and y are actually going to be TensorFlow placeholders. What are TensorFlow placeholders? They are gateways into our computation graph that we can input data into. Now I wrote this, by the way, because this is so new that there was not like a benchmarking script, so I just wrote this. Okay, so y is also going to be a TensorFlow placeholder, and we're going to input data into each of these in a second. So there are 100 possible values that are going to be here. Okay, there are 100 possible values. Now we'll initialize our TensorFlow session, our computation graph, with the tf.session function. Remember, none of this is TPU yet. We're about to convert it into TPU code. So inside of our TensorFlow session, we're going to start a timer to clock some performance here. Now, what are we going to do? We're going to compute a result by saying session.run. So inside of the computation graph, run this add operation on both x and y. And what are we going to feed in as our data into these placeholders? Well, using the feedDict parameter, we'll say, well, for x, we're going to input a value between 0 and 100 using the arange function of NumPy. And for y, we're going to do the same thing, a value between 1 and 100. Okay? Hold on, let me make sure that is going to be back there. Good, all right. So there's that, feedDict. Let me make sure it's all good here. Okay, now, once we compute that operation, so basically we're taking two arrays between 1 and 100, so it's just 1 through 100, each of those values, and we're just adding them all up. So the result is going to be 1 plus 1 is 2 is going to be the first value. The next value is going to be 2 plus 2, 4. So 2, 4, 6. That's going to be the result. And it's going to be 100 of those in an array. And we'll end the timer here. That's all we want to do. And we'll compute the elapsed time, the end minus the start, and we'll print that out. How much time has elapsed here? And we'll print out the result as well so we can see what we computed. Okay? So let's see if this works. Of course not. See, I already knew. Okay, x Right. Okay. And this one goes like that. Feed dict equals. Okay. Like I said, 0, 2, 4, 6, 8. That is running on a CPU. And so this took 0.01 seconds. Okay? Now we're going to convert this to TPU code. You ready for this? So that is our TPU. So let's remember this benchmark here, 0.01. Now let's compare it to the TPU. Okay? So how do we do this? So in Colab, what we can do is say change the runtime to the, oh my God, there it is, TPU. Awesome. Save. Connecting. Please connect. You got to connect for me. Do not mess up. Google's watching this, by the way. They're here. They were actually helping me last night on DM on Twitter. They're like, are you sure about this? Maybe check this out. Da, da, da. So thank you, Google. Because they saw that I was doing this live stream. Oh, it's initializing. Oh my God, this is going to work. Oh, it's connected. All right, so TPU time, guys. So TPU address equals gRPC. So in Colab, we can actually, the TPU has a name. So we can call it using the os.environment variable. And we'll say Collab TPU address. Okay, address, that's the name. And once we have that, we'll say, well, what is the TPU address? Let's see what it is. TPU address is TPU address. Now, inside of our TensorFlow session, we will initialize the session using the TPU address, or the address of where it is. And now we can list all of the devices, which are the cores, the TPU cores, in that list of devices. And I'll print them out at the very end. Print TPU devices. Now let's just see if this works. Really? But I did define OS. Did I not? Did I not? Really? Okay, fine. Fine. All right, import OS. Did I really not? Okay. Let's just import everything again. TensorFlow as TF. Okay. It's busy. It's busy. It's got that TPU. It's got that TPU. So there we go. We are connected to our TPU. And now we're going to do this. So we'll do the same operation we did before. And I'm going to take questions after this. So just start asking questions right now, guys. Now, I'm just going to do the same thing I did before, where I have this add operation, okay? But the different, and I'll do the same thing as up here. By the way, so when I said I wrote the code, I wrote this TPU versus CPU benchmark. It was based off of Google's original code, but there was no like TPU versus CPU version. There was only a TPU version, so I converted it between both so we could see the difference. Okay, so where were we? So the TPU operations here. So what we're going to first do, and here's an important bit, or we're going to rewrite that add operation for the CPU specifically with this rewrite function. Now, like I said before, TPUs are running on the systolic array hardware architecture. So we have a multiply and accumulate operation that is specific to the TPU. And in order to be able to compile down using the XLA compile time environment, we need to convert it into an XLA-friendly format of matrix operations, and that's what rewrite does. So once we initialize our TensorFlow sessions, we'll do this in a try finally loop. We'll say session.run, and well, the first thing we're going to have to do is initialize this system. Okay, that's the first thing we have to do. And then we say, well, let's start the timer. And we'll print out the results of what happens when we say run a session using those TPU operations. We're going to feed in the same deal. So it's going to be the numpy.arange between 0 and 100, 1 and 100. And for y, it's going to be np.arange between 1 and 100. And right, that's it. That I think is it. So then once we have that, now we can end the timer by saying end time. We'll count the amount of time that has elapsed since we started. So elapsed equals end minus start. And we'll print the elapsed time. Now, that's it for that. And then in our finally loop, make sure finally is here. Finally, we will shut down the system. So this is necessary. We have to, when we're using the TPU, we have to shut down, we have to run this command after we are done with our computations. And then we can close the session. Okay, let's hope this works. It's not going to work, but let's hope it works. Of course. So, okay. Why would that be invalid syntax? Invalid syntax on line 14. Oh. Right, okay, so print session.run Tpu Operations x, y, one more, I think, right? Okay. I really hope this works. I really hope this works. See, this is what live is all about. Either I'll make a fool of myself or, okay, here we go. Time is not defined. Yes, it is. Okay, fine. So I think it's like time is not defined. So import time, import time. NP is not, okay, so I guess import TensorFlow as well. Might as well. Come on. Yes. Really? It has no attribute shutdown system? Oh, because of this. Okay. Yes. Oh, tf.contrib.tpu.shutdown system. All right, start asking questions. I'll take some questions in a second. And I think this is finally going to work. Yes. Good. Okay, so 0.016 on the TPU versus, where were we before? 0.011. So actually, the GPU was faster. So this is actually, oh no, yeah, the GPU was faster. So this was actually a GPU versus TPU comparison. The GPU was faster for this extremely small operation, this add operation. So my point here is to have done two things. One, to demonstrate that you can use the TPU, and two, that when it comes to small models, like what we've just done here, it's not like TPU is like the be-all, end-all, right? It's got a specific use case. So now let me take some questions. Can TPUs process neural networks made with Keras? Yes, we'll do that at the very end. One more question. What is the next big thing after TPUs? It's quantum computing. So I'll have more to say on that later. So that's it. Quantum. Unleash the quantum. Anyway, it's all about having a wide variety of different types of chips And they all do different things. Quantum chips are good for specific tasks. TPUs are good for neural networks. CPUs are good for sequential tasks. GPUs are good for rendering. And just all together, we can use them for AGI, artificial general intelligence. But not to get, anyway. Check out Jerome Lanier, by the way. Great philosopher. So that was it for the Q&A. And now there are some key, let's see how much time we have. There are some key TPU functions in TensorFlow that I'd like to talk about right now. Okay, so the first one that you should know, there are three. The first one is the Tpu Estimator. Okay, so estimators are application level constructs in TensorFlow, right? So they apply to any, let me just minimize this. They apply to any kind of model, but we can use TPU specific estimators using this command right here, or function right here, Tpu Estimator, for TPU specific logic. Now, standard estimators are good for CPUs and GPUs, but TPU estimators are made for TPUs. And so this is what it looks like when we build that. Now notice that one of these parameters is this config parameter. So using this tpu.runConfig, that's the other TPU specific object that we have to create. And so we can do that using this tpu.runConfig function. And we give it the evaluation, the model directory, the session configuration, and the TPU configuration. And the third is the cross-shard optimizer. So like I said, that 1% we're talking about calculus, it's right now. So neural networks are models built with linear algebra, and they're optimized with calculus using gradient descent, for example, the most popular optimization strategy in neural networks that I won't go into. Just search gradient descent Siraj and you'll find like 50 videos on it. But gradient descent works on TPUs. All sorts of optimizers work for neural networks, work on TPUs, as long as they are made for neural networks, specifically Atom. There's a bunch of optimizers there, variations of gradient descent. But the TPU uses a specific technique called all reduce that I need to actually learn more about. And I'm not going to pretend to know all the details about all reduce because it's a very specific technique. And we can't just fit literally everything into this video. And I'll talk about TPUs more later. But what we know is that the cross-shard optimizer is made to take an existing optimizer and optimize it for the all reduce algorithm to aggregate the gradients. The gradients are the direction, these values that are vector values that are used to update our weights in whatever direction we're optimizing for. And it broadcasts the results of each of these gradients to each shard in each TPU core. So what this looks like for us as developers is we'll build our optimizer just like normally, and then we will wrap it using this tpu.cross-shard optimizer. That's the difference. And then we just do the rest. And so that's really the main differences here when we're building TPU-specific models. Now, of course, there are a few other little changes. So evaluation, metrics, and TensorBoard, you have to use specific TPU code for each of these things. And the TensorFlow documentation is great for that. But those are the three big ones. Now, one more benchmark here. Okay, so image classification with CFAR. Okay, so CFAR is an image classification data set, and the problem setting here is given an image, classify what it is, a dog, a cat, a car, whatever it is. This very standard task in machine learning. Now, the standard neural network architecture to solve this is a convolutional network, but for the sake of this demo, we're just going to use a linear, a multi-layer perceptron, okay? And we'll compile it on both the GPU and the TPU to see the difference in performance and in the code and how that changes. So if we look here, we can see the dependencies. And so I already have it written out, and I'm going to modify it live. So, and hopefully it works. So what we see here is us importing TensorFlow. We're importing TensorFlow and Keras. And so we have our basic multi-layer perceptron MLP model that we built right here, okay? Input times weight, add a bias, activate. Input times weight, add a bias, activate. That just keeps repeating, okay? And we have some special tricks here, fully connected layer, batch normalization, an activation function, and dropout, okay? So what we do is once we've built our model, we'll say, okay, Let's get our CFAR code using this load data function, and let's build our model. Let's use those two functions we just created, and then compile it using Atom, which is a gradient descent technique, and then we'll fit that model on the training and testing data. Now, when we do this on the GPU, let's run this code, and then we'll modify it for the TPU. So we'll save that. Hopefully this works. You never know. You never know. You never know. Never know. Okay. So let's see what happens here when we train this thing. It's going to download this data, and let me answer some questions while it's downloading the CFAR data. When is the wrap? The wrap is at the very end. The wrap is a reward for those people. It's a long-term reward for those agents who are optimizing for that reward to get into reinforcement learning. At the very end, we're almost there, okay? Will the free tier of Google Colab be faster than running it locally? That's a good question. So Google Cloud offers TPUs as well. So we can use the Google Cloud console to run our models in the cloud. It doesn't have to be with Colab. Just for teaching purposes, we're using Colab right now. But it doesn't have to be, and yes. Okay, so happy birthday, Harsh. Okay, that's it for the questions while this is downloading. So this is actually going to take a while. So while this takes a while, I'm actually going to turn this into TPU code. Okay, let me turn this into TPU code now. So to convert this into TPU code, what do we do here? So we're still going to have our model just like before. The difference now is we're going to say, let's do that. First is we're going to apply that cross-shard optimizer that we talked about before. So we'll say optimizer equals tf.train.atom optimizer, just like we had, right here. And the learning rate is like it's right here, 1. Okay. Now, what's the difference? We're going to create our TPU optimizer. Now, how do we do this? Remember, like I said before, we have to use that cross-shard optimizer and wrap our existing optimizer around that. And that is what we use to train our model, the TPU optimizer. Okay? Now, there's that bit. But before we train our model, we have one more thing to do for Collab, which is to say that we're going to connect in Collab to the TPU that we have inside of this virtual environment. And we want to use a cluster, okay? We want to use a cluster of TPUs, not just a single TPU. So we'll use the cluster resolver. So what the cluster resolver is it's letting us access a pod, right? So TPU pods are clusters. TPU gRPC URL, the one we just defined. And then we'll say, well, what is our strategy? So it turns out that Keras has a specific type of distribution strategy for that pod and we can call that using TPU Distribution Strategy. And we'll use the cluster resolver as the parameter to that. And now that we've done that, we can say, let's take our Keras model and convert that to a TPU model using the Keras to TPU aptly named function. And we'll use a strategy of the one we defined. Strategy. And that's it. Okay? So this is actually going to take a while to download. So what we'll do actually is pause this, okay? Because it's going to take, this is live, and we just want to see if this compiles. And it's not going to compile because the runtime is GPU. But if we set the runtime to TPU and save that, let it connect, we just want to see if this compiles, this TPU code. Let me fix this and then I'll answer some questions, okay? So invalid syntax where? Strategy equals strategy. Oh, of course. Winning, okay. Good, so there. This TPU code, that was us converting it into TPU code. This is in Keras. Okay, so we're not gonna sit here and wait for it to download the data and train and et cetera, but that's how that goes. Now, Google has this default train Shakespeare in 5 minutes example that we'll find right here. And what this does is it uses Keras to train a recurrent network to generate speech in the style of Shakespeare. So the input data are Shakespearean texts, like these poems. Loves had led me, no dumbs lack her. It doesn't even make sense. But let's just go through this very quickly. We're downloading the data from Project Gutenberg. We build that data. In Google Colab, we have a specific address for the TPU. Okay? We're doing some data transformation. None of it is TPU specific, it doesn't seem. None of this is TPU specific. We build our model. This is a long short-term memory network, a type of recurrent network made specifically for long-term sequences like giant corpuses of text. And LST, just search LSTM Siraj for a video on that. And yeah, nothing TPU specific here yet. When we train the model, here we go. Like we did before, TPU.Keras to TPU model. So it's resolving to the MAC multiply accumulate architecture, the systolic array architecture for the TPU. We're fitting it, they train it, they make predictions with it. None of it is TPU specific. And here are the results. Okay, so it's actually very simple to use a TPU now, and this is a first. So thank you, Google, for releasing this. Let me answer some questions, and then that's it for this live stream, and we'll wrap as well. This is a part of Move 37, yes. Can we get a link to your Collab file? It's in the video description. It's an IPython notebook. You can then upload it to Google Colab because it's backwards compatible. And last question, will Google make more money through AI than advertising in the future? Advertising is done by AI. Let me just end this with a very important thing that needs to be said. AI is everywhere. AI is manipulating all of us. AI is normally with advertising, with billboards, it's a one-way, speaking of that, with billboards, it's a one-way, with billboards and with ads that we see in real life, it's a one-way relationship that we see the billboard and we decide if we want to buy it or not. But with the internet, with AI, when we see an advertisement online, it's going to measure what we do in relation to that advertisement and then subtly show us something different to manipulate our behavior such that we will be more likely to click on that ad the next time. So we're all subtly being manipulated by these AI algorithms because that's how the business model works for these social media giants. And that's just how it works right now. But we've got to get to a world where our AI algorithms are not optimizing for our attention for the sake of this third-party advertiser, but instead for our time well spent. AI algorithms that benefit us. And that's a new world that we're heading towards. And it's a beautiful world. And we all at School of AI envision that world. And we will get to that world, I promise you. But one step at a time. And thank you for being here. And thank you for being a part of this community. So there's a lot of exciting things that are coming out of AI. Like any power, like fire. Fire can burn us, or it can be used to give us warmth and to sustain us. In the same way, AI can be used to manipulate us and distract us and control us and polarize us. But it can also be used to bring us together to solve some of the hardest problems in the world and make the world a better place. And we at School of AI are determined to make the latter reality our reality. So thank you for being here. It's been a pleasure. And let me just end it with a wrap because I promised a wrap. So going from a little serious talk to a more fun talk. Looks like my YouTube app is I'll just go a cappella. I like, okay. I want to close this at 59 minutes. And I just want to leave you with that thought, actually. Let's not be silly at the end this time. Let's be a little serious and say, you know, this is something that needs to happen. That's it for this live stream. Thank you guys for showing up. For now, I've got to go do a bunch of School of AI work. I have some great content coming out for you this weekend on how I'm so productive. So you better watch out for that. It's coming out on Sunday or Monday, and another video as well that I'm going to keep close to the chest. So thank you guys. I love you.